Okay, hi everyone. So in this screencast, we're going to do a couple of things. We're going to finish out the indeterminate limiting forms, and then we are going to derive the inverse trig derivative rules, and then from there we will introduce a brand new topic. So the first two are fairly quick. So we know what to do with these 6 indeterminate forms up top. Okay, and this is kind of the order in which we did them. We had the L'Hopital indeterminate forms, we then had the kind of one step away from being L'Hopital, and then we kind of grouped these 3 together, okay? The indeterminate form that remains is positive infinity minus positive infinity. And notice here, it is positive infinity minus positive infinity as a limiting indeterminate form. If it was something like positive infinity plus positive infinity, this limiting form is not indeterminate. Whichever one wins, so to speak, the battle doesn't change. Similarly, if it was negative infinity plus negative infinity, this also doesn't change. Interestingly, if I said negative infinity minus negative infinity, this is indeterminate, and hopefully you see that this is no different than, right? Okay, like these are all one and the same. So this indeterminate form is kind of captured in here. So here it does matter that it's positive infinity minus positive infinity. And if we think about the battle analogy, if the first positive infinity wins, the whole thing approaches positive infinity. If the second positive infinity wins, the whole thing approaches negative infinity. You may say to yourself, well, either way, doesn't the limit not exist, so don't we not care? And the answer is no. Well, the thing about indeterminate forms is if this battle wins, the whole thing approaches positive infinity. If this battle wins, the whole thing approaches negative infinity. But then there could be some kind of like a truce, right? There could be a point in between positive and negative infinity at which point the battle resolves. So it really is quite involved. All right. So and of course, when I say quite involved, I hope you kind of found some sarcasm there, because a point between positive infinity and negative infinity literally takes up all possibilities, and you're saying to yourself, well, that doesn't help me at all. So the first limit we're going to consider is the limit as x approaches 0 from the right of 1 over x squared minus cos 3x over x squared. And the first one we'll do is one that's, fairly straightforward, that you can see what's happening here. First of all, as x approaches 0 from the right, this quantity here does approach positive infinity, minus cos of 3 times 0 is cos of 0. This is equal to 1. Positive 1 over something approaching 0 from the right is going to approach positive infinity. So you first acknowledge this is indeterminate. Now, this indeterminate form is similar to this indeterminate form in that your goal is to rewrite the argument in a form that will require, or that will allow L'Hopital's rule, okay? But I'll be the first one to tell you that between these two, this one tends to be more of a pain to just figure out just exactly the right way to get it into an indeterminate form that allows you to use L'Hopital's. You'll notice a couple of themes that come up, however. In this case, the common denominator is pretty deliberately obvious. And if I take a look at this and I rewrite this as a quotient, okay, what I try now is, as x approaches 0 from the right, this does now approach 0 over 0, which is now a L'Hopital indeterminate form. And you would proceed from there, okay? At that point, I think I know you know what to do. The way these tend to get tricky is when you have an infinity minus infinity, and you wonder to yourself, well, how on earth do you get the two terms into one? So one thing you're seeing is if you have, two fractions, to write the expression as one fraction. I'm going to start just plucking some from your book here. Some are just truly dirty tricks, and I'll show you one that is a trick that I assure you will never see in any kind of formal setting, because it really is quite dirty. Well, no, sorry, not this one. It's going to be the next one after this one. So let's call this example 1. Example 2 is reasonable. All right, let's take a look. Ready? Here's the limit. The limit as x approaches positive infinity of ln x minus the natural log of 1 plus x. And as x approaches positive infinity, ln x approaches positive infinity, and natural log of 1 plus x also approaches positive infinity. This is an indeterminate form. Well, how do we write this as a quotient? And as we keep seeing over and over again, more and more often as we get further into calculus, we are noticing that, yes, everything really does come back. There is our old friend, property of logs. Log base e of x minus log base e of 1 plus x can be written as the natural log of x over 1 plus x, okay? And then what's interesting here is I've rewritten this as a quotient, and as x approaches positive infinity, here's what's interesting. As x approaches positive infinity, look at the argument of the natural log. It's a rational expression. As x approaches positive infinity, this rational expression will approach 1, and the natural log of 1 equals 0. Look at that. Okay. If you wanted to stick with the idea of indeterminate forms, you can do this. The limit as x approaches positive infinity of the natural log of x over 1 plus x, this limiting verb, this limiting activity is going to affect the argument of the log. It's not affecting the fact that we are going to be taking the natural log. So what I'm going to do is take the natural log through the limit and just say to myself, I can just first deal with the limit as x approaches positive infinity of x over x plus 1. Okay, here is where you can use old news or new news. The old news is remembering limits to infinity of rational functions, or you can go over here to the side and say limit as x approaches positive infinity of x over x plus 1. This approaches infinity over infinity. Then use L'Hopital's rule. In one iteration, you will have the limit as x approaches positive infinity of 1 over 1, which equals 1. Then you have, at the end of the day, the natural log of 1, which equals 0. Okay? Either way you go, you will still get to the right place. The key here was reconciling how do we somehow get a quotient out of the argument of the limit. How do we get a quotient out of the argument of the limit? And yes, everything comes back at us. So if you've been kind of doing your due diligence and, looking up things and refreshing when you can, this is when you have payback, as I've been saying to you all along. Okay? This is one where things can be particularly dirty. And I'm going to show you this and, let you see that yes, it is dirty. Okay, x squared plus x. And then we have minus x. All right. So here, as x approaches positive infinity, I think we'd agree that this square root approaches positive infinity. Okay. Minus and x, as x approaches positive infinity, will be positive infinity. So the question here is, my goodness, how do we get a quotient out of that? And, well, you think to yourself, where have I ever had, radical expressions before that involved me working with a quotient? And I'm thinking of our tall Thomas. Thomas, you said it in class at one point. What can we possibly do? And yes, you know what it is? It is this. We're going to multiply by 1. Multiply this entire limit, okay, by 1 in the form of the conjugate of the radical expression. So the square root of x squared plus x all over the square root of x squared plus x, right? This is just the number 1. And again, watching your algebra, the limit as x approaches positive infinity, okay, I have a difference of squares. So a minus b times a plus b, we get a squared, which is just x squared plus x, minus x squared, all over square root of x squared plus x. And we're going to have the limit as x approaches positive infinity, right, we're cleaning, I get x all divided by, all right, square root of x squared plus x plus x. Okay? Okay, now let's see what happens here. As x approaches positive infinity, the numerator approaches infinity, the denominator approaches infinity, and look what we have. We have now a L'Hopitalable indeterminate form. You would then use L'Hopital's and go ahead and see what happens. Okay, look what happens here. So here is when I use L'Hopital's. Be careful with this denominator's derivative here. Oh my gosh, I just messed it up. Whoa. Okay, sorry about that. So here's in the indeterminate form, here is the derivative of the numerator, here is the derivative of the denominator, and look at my cleaning. So this is the important part here, the cleaning part, our algebra. Here is this right here, okay? This right here is this. This 1 is in the denominator, so what I did was I got a common denominator. So now this whole denominator is right here. 1 divided by a fraction. Okay, 1 divided by this entire denominator, I just reciprocated. And here's what I've got. Now we're back in kind of old familiar territory. We have a quotient of expressions, and we have a limit as x approaches positive infinity. So we can talk dominant terms here, can't we? We can talk dominant terms, and we have numerator over denominator, right? And if we look at the numerator here, okay, the numerator, the dominant term is going to be 2x, okay? 2 root of x squared. Root of x squared just becomes 2x. Downstairs, there are 2 dominant terms. 2x plus, that's the 2x here, plus there's a 2x here. And this becomes the limit as x approaches positive infinity of 2x over 4x, which equals 1/2. Okay? So that's enough for indeterminate forms of this type. I will tell you that these tend to be on tests and even on the AP exam, quite frankly, though I don't like that to be a motivator for us at all. Our motivation is the challenge. This one tends to occur the least frequent, and when they do occur, they are generally speaking not dirty tricks. Okay, this here tends to be a little bit long and arduous. All right, so that was easy portion number 1, and I will make sure I give a homework assignment that kind of touches on all of these. We are now going to derive the derivative of the inverse sine function. And I'm going to start with this question. If y equals the inverse sine of x, what does dy dx equal? That's the question, right? Okay, so I'm going to start doing this derivation, but over here to the right, I'm going to say this. If y equals the inverse sine of x, right, we know this says the same thing as x equals sine y. Okay, these two statements are saying the same thing. They are equivalent. X equals sine y, y equals sine inverse sine of x. X equals sine y, I'm going to draw a picture here that I'm going to refer to in a moment. But if the sine of angle y equals x over 1, that means I can call this angle y, and sine y is opposite over hypotenuse. I can call this length x and the hypotenuse 1. Then I can call the leg here 1 minus x squared, just by the Pythagorean theorem. And I'm going to refer to that drawing a little bit. But y equals inverse sine x is my function. What does dy dx equal? Well, let's see. The first thing I'm going to do here is rewrite y equals inverse sine x as x equals sine y. Then I'm going to take the derivative with respect to x of both sides. And I could squeeze it in here. D by dx of both sides. You go ahead and do that and replay me. Okay? If you took d by dx of x equals sine y, you get here 1 equals cos y dy dx. You'd solve for dy dx, because after all, that's what I'm trying to find here. Dy dx equals 1 over cosine of y. But cosine of y is saying cosine of this angle y. The cos of this angle y is adjacent over hypotenuse. So at the end of the day, dy dx equals 1 over adjacent over hypotenuse. 1 over root of 1 minus x squared all over 1, or just the root of 1 minus x squared. So now, everyone, we have our next derivative rule. The derivative of the inverse sine of x equals 1 over root of 1 minus x squared. There it is, okay? Now, if I had, say, this question, what is the derivative with respect to x of the inverse sine of 3 ln x? Let's just kind of incorporate the chain rule into this new derivative rule. Go ahead and try it, and then replay me. All right, here it is. The derivative with respect to x of the inverse sine of blah, the inner, right? This is the inner. The derivative with respect to x of the inverse sine of the inner is 1 over the root of 1 minus the inner squared, right, x squared, times the derivative of 3 ln x, which is 3 over x. This right here is that derivative, okay? When we go to getting the derivative rules for the inverse cosine of x, the inverse tangent of x, okay, the inverse, so you have to do inverse secant of x, and the inverse cosecant of x, and of course the inverse cotangent of x. The derivation for all of these inverse trig functions is identical to that which I did above. Obviously not identical, because it's obviously not identical, but it's identical in its method. So I'm just going to give you then these derivative rules. Okay, here they are. And I color-coded them to help you with some with your memorizing. Notice how derivative of inverse sine and inverse cos just differ by the negative, right? Similarly, look at the derivative of inverse tan and inverse cotangent. They differ by a negative. And inverse secant and inverse cosecant also differ by a negative. Okay? So you now have the derivative rules of all your inverse trig functions. And ladies and gentlemen, therein concludes your derivative rules. You now have all of them, every single one. Okay. Now what I want you to do is, you'll notice that in the calendar, I had asked you to print something out and have it for this screencast, and I want you to get that out, please. Okay? And when you get that out, it should look like this, and you're going to write on that piece of paper. Okay? So here's what we have. We have this question. A 10-foot ladder is leaning against a house on a flat ground. The house is to the left of the ladder. The base of the ladder starts to slide away from the house. When the base has slid to 8 feet from the house, it is moving horizontally at the rate of 2 feet per second. Wow. What a bunch of information. Here's what I want you to do first. Do this with me. Let's go ahead and draw a picture of the situation. Okay, here's the wall of the house. Okay. The house is to the left of the ladder, so here is the house. There is a ladder. It is 10 feet long. Okay, this ladder is 10 feet long. The base of the ladder, right here, it starts to slide away from the wall, and someone seems to be dragging the base along the floor. And it is moving at, we're also going to make this little note to myself, 2 feet per second. How fast is the ladder's top sliding down the wall when the base is 8 feet from the house? Okay, here's what we're going to talk about. We've got some information here. This is a situation a problem that's going to really capitalize on us knowing what it means to take the derivative of the identified independent variable, okay? In a question like this, and these problems are called related rates problems, and you'll see why that nomenclature is actually incredibly informative. Questions like this are asking you to relate the way in which 2 or more dependent variables are changing as a function of time. So the first thing I'm going to tell you, and that you probably gleaned from my statement, is that time, after all, is the independent variable. And I could have gotten that without me even saying anything. I could have gotten that by looking at the fact that there is something changing as a function of time to feet per second, okay? The independent variable here is time. When the base has slid to 8 feet from the house, it is moving horizontally at the rate of 2 feet per second. I want you to think about this. If the base is being slid outwards along the floor at a rate of 2 feet per second, it is fair to say then that this distance here, I'm going to call this distance x, okay? X is the distance the base of the ladder is from the wall. I'm going to say that this 2 feet per second, yes, it is the rate at which this ladder is being dragged away. It is also the rate at which this distance x is changing. Or I can say this, x is increasing at the rate of 2 feet per second, which hopefully should make sense. If the base of the ladder is being dragged along the floor at a rate of 2 feet per second, that's the same thing as saying this distance from the wall is increasing at the rate of 2 feet per second. And I'm going to use some differential notation, or notation that involves derivatives. That is no different than saying dx by dt equals positive 2. Look what this is saying here, everyone. The rate at which x is changing as a function of t equals positive 2. Okay? Let's look at the question. How fast is the ladder's top sliding down the wall? Let's just stop right there, okay? How fast is the ladder's top sliding down the wall? I'll finish the sentence in a minute. This is asking, what is the rate of change of something? And if the ladder's top is sliding down the wall, I'm going to call this distance here y. Now, this ladder is 10 feet long. It's not going to change. Do you agree that as x is dragged along the floor, y is going to decrease, correct? How fast is the ladder's top sliding down the wall? Let's call that dy dt equals what, right? What's the moment in time that we are concerned about? When x equals 8. Okay? So in questions like this, you are often given a known rate, asked to find an unknown rate at a particular time in question. Okay? Notice here that y changes as a function of time. X changes as a function of time. X and y are the two variables dependent on the independent variable time. So what characterizes questions like this is the fact that time is the independent variable. There is, generally speaking, a known rate and an unknown rate, okay? So then the way you solve these questions, everyone, is you say to yourself, okay, I have all my information in this picture, and step one, and I'll give you kind of a very nice 4-step rule, generally agreed upon rule that allows related rates questions to be very doable. Identify a picture that represents a scenario. Incorporate variables that can somehow describe those things that are changing over time. Notice the ladder is not changing as a function of time, the ladder's length. This is changing and this distance is changing. Identify the known rate and the unknown rate, okay, that you're asked to find. Here is the next step. These are my dependent variables, y and x. Relate them. Given this situation, is there an equation that relates x and y? I think you probably all see it. This is, through no coincidence, a right triangle. X squared plus y squared equals 10 squared. Okay? We now have an equation that relates the dependent variables. Now we're going to take the derivative of this equation. And here's where that exercise in class a couple of days, I hope that you're all like saying, I hope you're not all moaning that the screencast is 24 minutes and 59 seconds long, but I hope you're saying, oh, I remember this. When I take the derivative of this equation, I have to take the derivative with respect to the independent variable. And what's the independent variable here? It is time. So I'm going to take the derivative with respect to time of x squared plus y squared and the derivative with respect to time of 100. And what I get here is 2x dx dt plus 2y dy dt equals 0. Okay? This equation right here is called the equation involving derivatives, or this is called the differential equation. Okay? This is the differential equation. I sometimes just call this like the variable equation or the equation that's describing that which is varying. We are now going to use the differential equation to find the unknown. The question here was dy by dt equals what at the precise moment when the base of the ladder is 8 feet from the floor. Okay, well, let's see. We have to use our differential equation to sub in that information about x dx dt, y dy dt at the moment when x equals 8. Okay, well, let's see. When x equals 8, let's see, I get 2 times 8. Do I know what dx dt here is? Yes, dx dt is a constant positive 2 feet per second times positive 2 plus 2 times, I have to find the value of y when x equals 8, right? That's the time. We need to find the value of y when x equals 8. How do I do that? Let's make a little note to self. Need y when x equals 8. Well, when x equals 8, 8 squared plus y squared equals 10 squared. Or y squared equals 36, or y equals 6, right? That's from the Pythagorean theorem. So now I know when x equals 8 is the same time when y equals 6. So 2 times y times dy dt when x equals 8. Oh, good. That is what I'm looking for, my unknown rate. Okay? Now I'm going to solve this for dy dt. dy dt equals negative 32 over 12, which equals negative 4. No, that's just downright offensive. Negative 8/3 feet per second. Okay, now this makes sense. First of all, the fact that dy dt is negative, it better be if the ladder is going to be falling down the wall, right? This is dragging down this way, so y is decreasing. Okay, so dy dt equals negative 8/3, and what's very important in related rates questions is we always include the units so that we know, the reader, that you know what that number means in the context of the problem. Okay, we're going to do a couple more together because this screencast is yes, I know it's going to be long, but it's also I'm wrapping part of homework in this. Okay, let's do one more together. And then I'll give you kind of your 4-step, and then I'll give you the rest of the homework. Please open your book, if you will, to page 208. I think it's 208. Let me just double check on that. Is it 208? Yes, go to page 208, please. Okay, number 12. Let's read it together, and we'll do the setup together, too. Okay, number 12. A stone dropped into a still pond sends out a circular ripple whose radius increases at a constant rate of 3 feet per second. I'm immediately going to write this down. dr by dt equals positive 3 feet per second. Okay. How rapidly is the area enclosed by the ripple increasing at the end of 10 seconds? All right, that question right there says, how rapidly is the area enclosed by the ripple increasing? That that translates into dA by dt. This is the rate at which the area is increasing as a function of time. dA dt equals what at the particular moment in time t equals 6. Okay? So related rates question. Generally speaking, a known rate and an unknown rate. Independent variable is time. The question is, in this context, if I look at the dependent variables, is there an equation that relates A and R? Yes. Area equals pi r squared. Okay? So we are now going to take the derivative of this equation, and when I look at this equation, just make sure the variables are indeed variables. In other words, they vary as time elapses. And in this case, as the ripple ripples out, R increases and A increases. That makes sense. The derivative with respect to time. Take d by dt of both sides. You will get dA by dt equals 2 pi r dr by dt. Now we use a differential equation to solve for my unknown rate. Look at that. That's my unknown rate. dA by dt equals 2 pi. Okay. What is r at the moment when t equals 6? Well, let's see. If the radius is increasing at a constant rate of 3 feet per second, at t equals 6, I'm going to say, well, at t equals 6, this is the same moment when r equals then 18 feet, right? If the radius is increasing at a rate of 3 feet per second, then naturally, at the end of 6 seconds, the radius will be 18 feet. And there, that gives me my r value at that moment in time. What's dr by dt at the moment in time? Well, dr dt is a constant 3. At the end of the day, when I multiply out 2 pi times 3, it's going to be, what is that? 19 times 3, is that 57? 57 pi. Okay, what are the units here, everyone? This is the rate of change of the area of a circle. An area of a circle, if the radius is in feet, this is going to be square feet per second, right? Okay, that's a related rates question. Related rates. What is the situation? What is the unknown rate? What's an unknown rate? What equation relates the dependent variables? Differentiate that equation, and you know we differentiate with respect to the independent variable time. Input into the differential equation those values of the unknowns, and those unknowns could be variables or they could be unknown and known rates at the moment in time in question to solve. All right, let's do another one. Let's do this. Let's do question number, let's do this one. Ooh, let's do 24. 24 is all you. What I want you to do for 24 is just set up what you think, let's see, just do the equivalent of this part, which means identifying the known rate, identifying the unknown rate, and setting up the equation of dependent variables, and then replay me. We're doing number 24. Okay, this is the picture in black here is the picture in your book. This is my plane. No judgment, please. The plane, you're told, is flying this way at 300 miles per hour. Okay? Part A says, how fast is theta decreasing at this instant? D theta dt equals what? And what instant is he talking about? At the instant when theta is 30 degrees. That is the question. But I also know that a known rate here, if the plane is traveling at a constant speed of 300 miles per hour, I know dx dt is always positive 300 miles per hour. Okay? So now the question becomes, can I relate theta and x, my two dependent variables? One thing I want you to notice here is this 4,000, that's a constant, right? This 4,000 does not vary, right? This 4,000 stays the same because the plane forever just travels horizontally. So the equation here that I'm going to use is tan theta equals 4,000 over x. Now take the derivative with respect to t. and you see that I automatically rewrote tan theta equals 4,000 over x as tan theta equals 4,000 x to the negative first. Now I'm going to take the derivative with respect to t. The derivative of tan theta is secant squared theta d theta by dt equals negative 4,000 x to the negative second dx by dt. Okay? Now I'm going to start inputting into this differential equation information about the particular moment in time so I can solve for d theta by dt at that moment in time. Well, when theta equals 30 degrees, the secant squared of theta is going to be the cosine of theta reciprocated and then squared. See how everything's coming back at us? Side note, cos of 30 degrees equals radical 3 over 2. So secant is 2 over radical 3. Square, we get 4/3. d theta by dt equals negative 4,000. Okay, what is x when theta equals 30 degrees? Well, let's see. At 30 degrees, tan of 30 degrees equals 4,000 all over x, right? This is us doing the work to find information about the variable values at a particular moment in time. That's what we're subbing into our differential equation. X is going to equal 4,000 over tan 30 degrees, which is 4,000 times 3 over root 3, because tan 30 is radical 3 over 3 multiplied by the reciprocal. Whoops. This becomes 12,000 over root 3. Okay, and let's see. Oh, look at this. Goodness gracious. We have to then find x and then raise it to the negative 2. So this number reciprocated and then squared. We get 3 all over 12,000 squared. We'll clean that in a second. And what is dx dt? dx dt is 300. Okay? When I go and solve this, and this actually isn't that bad because we're going to have some things canceling very nicely, I get d theta by dt equals, let's do this in together, negative 4,000 times 900, all divided by, I'm going to do it this way, so I'm going to start canceling zeros with glee, times 3/4, right? Okay, here we go. 100 there, 100 there, 1 there, 3 there, 3 and 3. Is that 9 and, did I cross out these? Yeah, 9 and 120. This becomes 9 over 120 times 4. Well, that wasn't that bad at all. 3 goes into 3, 3 into 40, 40 times 4 is 160. Can't forget the negative. Negative. Look at that. d theta by dt equals negative 3 1/60th radians per, what's the independent variable time? Radians per hour. Look at that. Look at that. That was fantastic. Okay, I think it's good. I think it's time for me to give you some homework now to do on your own. Related rates, right? Draw a picture if you need to. I didn't draw a picture here about the plane. The plane was given to me. Draw a picture, identify the known rate and the unknown rate, relate the dependent variables in an equation, and then differentiate with respect to time. The reason why these kinds of questions are called related rates is because, look, at some point you will get rates right here that are related somehow through some relationship, some equation, right? A rate or rates, right here, look at this equation. This is the particular relationship between these two rates because this, after all, right, we know that this describes a rate, an instantaneous rate of change of r as a function of time, an instantaneous rate of change of area as a function of time, right? Here we go. Another one. Here he is. Here's this one. This relationship between rates. So these questions are called related rates. All right. That is probably the longest screencast ever. And I'm going to give you the homework that goes with this, and it's going to be pretty light because, you know, you've done quite a bit already. And I will put it down here. Or no, you know what? I'll put it in the teacher page.